Hello everyone, my name is Soroosh. I am a PhD student at Concordia University. I'm presenting this paper on behalf of my supervisors, Dr. Arash Mohammadi and Dr. Amir Nasif. The title of my presentation is Siamese Neural Networks for EEG-based Brain-Computer Interfaces. The scope of our research is on BCI systems. BCI systems introduce a new communication medium to individual's brain and can boost their performance or can help humans to compensate for their lost functionalities by having a new communication medium. So BCI systems are developed based on the plasticity properties of brain. To develop a BCI system, we need to monitor the brain activities. And in this work, we're using electroencephalogram or EEG. And more specifically, we are trying to develop a motor imagery-based BCI system. So motor imagery is the case that we are thinking of having a movement in our limb, but we are not actually doing that. And based on the neurophysiology, we know that we can see the patterns and the signatures of the motor imagery in the EEG signals. The patterns are called ERD, event-related desynchronization, and event-related synchronization, ERS. So basically, our goal is to find out these two signatures in the signals. Here we have the signals, the EEG signals, and we can clearly see the ERD and ERS. On left, you can see that slow decrease in the power and fast increase in the power. So the first part is ERD and then the next part is ERS. And on right, you can see the spectral temporal representation of the EEG signals that have ERD. Okay, so but the problem in EEG processing is that EEG signals are so noisy and extracting the information that we are looking for is really hard. So we need to come up with sophisticated processing frameworks for this purpose. What you're doing and the approach that we're taking in this work is metric learning. So in metric learning, we are designing a neural network that can abstract and extract some embeddings or features out of the signals, EEG signals. And then the purpose of metric learning is to manage the features in a way that we have maximum distance for interclass features and a minimum distance for features from the same class. Okay, so, but here is the thing that metric learning is not necessarily developed based on distance. We can have the same thing for similarity. It depends on the objective function that we are using. So in this topic, contrastive loss, triplet loss, and n-pair multiclass loss are really famous objective functions that are proposed in the literature. And in this work, we're going to use contrastive loss. To use contrastive loss, we have to come up with a new architecture for our neural network, and we have to use Siamese neural architectures. So to formulate our work and in EEG processing with Siamese networks, first of all, we denote each EEG trial with X, with metric X, with a number of channels multiplied by number of samples. And then after that, we apply a pre-processing on the signal, so we get ZK. The pre-processing is removing power line interference and also having a bandpass filtering of the signals in the range of 7 to 30 hertz. So when we extract the embeddings out of the network within GWZ1 and GWZ2, contrastive loss is actually measuring the distance between the embeddings. So the distance here is Euclidean distance. As you can see in equation 1, we are measuring the Euclidean distance. For Siamese networks, we need to come up with a label, Y. So Y is denoting that if the two inputs are of the same class or not. Okay, so this is the only thing that we have to do. To summarize, in equation 3, we have the contrastive loss function. As you can see, we have a new parameter here, or hyperparameter here. It's called M. M is denoting a margin between the two classes. We need to set some values greater than 0 here to have a safety region between the two classes. All right. So the next part is how we can use the Siamese network. So Siamese network, as you've noticed so far, are developed mainly for binary classification problems. Actually, we can use them for multi-class problems, but it's really hard when it comes to training, and it has its own problems. Poor local minima and slow convergence are really famous problems with contrastive loss. So in this work, because our motor imagery classification problem is of 4 classes, we are using some techniques to decompose the multi-class problem into a number of binary problems. So we are using the OVO and OVR techniques. OVO stands for 1 versus 1, and OVR stands for 1 versus rest. So based on the coding matrices that you can see here, for let's say OVR technique, we have to design 4 different classifiers that are are trying to classify the supersets that we can see based on zeros and ones in each column. So here is how we have to define the supersets. All of the items, all of the trials denoted by 0 form the superset S0J, and all of the trials denoted by 1 form the superset S1J, and all of the items denoted by 2, they are not participated in the classification. So we form the supersets, and we use these 2 supersets to train each of the classifiers. Each of the classifiers, I mean each of the Siamese networks. So for OVR, we need to train 4 different classifiers, and for OVO, we need to train 6 different classifiers. Here is the algorithmic approach that we have. And here is the neural network that we have. Please pay attention that in this work, we are using the covariance matrices of the EEG trial as the input to the system. So that's why the input is of size 22 by 22 because of the EEG signals. They have 22 channels. And you can see the details of the network in the caption. The data set that we have used is from BCI competition 4, 2A. It has 4 classes: left-hand MI, right-hand MI, feet MI, and tongue MI. And 22 electrodes are used. The sampling frequency is 250 Hertz. And we have 72 epochs for each class. So here we have the classification accuracy, and we have compared our framework with state-of-the-art accuracies in the literature on the same data set. As you can see, Siamese OVR is outperforming the OVO approach, which is interesting. And we have fairly well performance compared to other techniques in the literature. And here we have the pairwise classification accuracy, and that we see. So when it comes to pairwise, it's not multi-class anymore. So we are not using OVR or OVO. It's just the Siamese network itself, one Siamese network. And you can see the performances that we have calculated here. So this work is just a proof of concept that we can use metric learning techniques in EEG processing. And this is just the building block and the first step for our future research. If you have any question, please forward it to the following two emails. And that's it. Thank you so much for your attention and hope you enjoyed